Find the HCF of 25 and 45 by ED. ED is nothing but Euclid's division, the same also called as Euclid's division lemma or simply division algorithm. So first take the given two numbers and to do normal division, 25 and 45. 25 ones are 25. 45 minus 25 is 20. So write this in the form of A equals to BQ plus R. That is nothing but dividend equals to divisor into quotient plus remainder. Now again from this step pick remainder and divisor. Again do the division, 20 and 25. 20 ones are 20. 25 minus 25. Let us write this also again in the form of dividend is equals to divisor into quotient plus remainder. Dividend 25 equals to divisor into quotient 20 times 1 plus remainder 5. Now again from this step, as usual like the previous one, we need to pick the remainder and a divisor and do the division of those two numbers, 5 and 20. If you do division, 5 4s are 20. 20 minus 20 is 0. So we can write this step as dividend 20 equals to divisor into quotient 5 times 4 plus remainder 0. So as soon as we get the 0 remainder, we need to stop the process here. So after getting the 0 remainder, what will be our divisor? That will become our HCF. So in this case it is 5. So HCF of 25 and 45 is 5. Moving to the question number 2. Find the HCF as well as LCM of 25 and 40 by prime factorization method. So first let us do the prime factorization of the given two numbers 25 and 40. 25, 5 5s are 25, 5 1s are 5. Then coming to the next number 40. 40 will come in 5 table as usual. So 5 8s are 40, 2 4s are 8, 2 2s are 4, 2 1s are 2. So this is the prime factorization. So let us write this here. 25 is equals to 5 times 5. 40 equals to 5 times 2 times 2 times 2. That's it. Now if you observe this, from these two, which is common here, number 5 is common. Except 5, nothing else is common. So our HCF is 5. From both the numbers, after doing prime factorization, which one is common, that will comes under HCF. Then what about the LCM? First write the common one as it is into whatever extra remaining, that all you need to write here. Here 2 is extra, so write that 2. Here one more 2 is extra, so write that 2 also. Again one more 2 is extra, write that 2 also. Here 5 is extra, so write that also. Now if you multiply all this, 5 2s are 10, 10 2s are 20, 20 2s are 40, 40 5s are 200. So HCF of 25 and 40 is 5 and LCM of 25 and 40 is 200. Question number 3. Finding whether a given fraction or rational number has terminating decimal or non-terminating repeating kind of decimal. So how we will find out whether a given rational number has a terminating decimal or non-terminating decimal? That depends only on the denominator. So in the denominator, if 2 is there or 5 is there or 2 and 5 both are there, then we can say that it has terminating decimal. So what exactly is 2 5 2 into 5 means? In official we will say it as if the denominator is in the form of 2 power n into 5 power m, then we can say that it has terminating decimal, otherwise non-terminating decimal. So that only in short form we will say it as, in the denominator only number 2 should be there, or only number 5 should be there, or both 2 and 5 should be there. Except these numbers, nothing should be there. So then we can conclude that it has a terminating decimal. So let us check one by one now. Here the first question he gave it as 1 by 2, right? So in the denominator we have only number 2, except 2 nothing else is there. So I can clearly say that this has a terminating decimal because the denominator is in the form of 2 power n into 5 power m. How you may get that out, where it has only 2, then where is 5? For that we will do is 1 by 2 as it is into I am writing it as 5 power 0, because 5 power 0 is 1. So if you multiply with 1, nothing change will be there. Obviously it will be 2 only. So that's the reason the denominator is in the form of 2 power n into 5 power m. Next, question number 2, he gave it as 3 by 10. That is equals to 3 by, in the denominator we have 10, and 10 is not a prime number, so we need to write it as the prime numbers. So 10, I am writing it as 2 5s. So now if we observe in the denominator we have only 2 and 5, or else if the denominator is in the form of 2 power n into 5 power m, so I can conclude that this is also has terminating decimal. Next, question number 3 is 7 by 5. Question number 3 is 7 by 5, that is equals to 7 by 5. I am writing it as 5 ones are. So that is equals to 7 by 5 into 1. In the exponents and powers we have one formula, any number power 0 is 1. So I am replacing this 1 with any number power 0. So that I am taking as 2 power 0. So now I can say that the denominator is in the form of 2 power n into 5 power n. So it has a terminating decimal. Next, coming to the question number 4. 11 by 40. So here 11 as it is, by 40 is not a prime number, so let us do prime factorization of 40. 40 can be did as 5 8s are 40, 2 4s are 8, 2 2s are 4, 2 1s are 2. So 5 power 40 is nothing but 5 times 2 into 2 into 2. 5 times 2 into 2 into 2. So now if you observe the denominator clearly, we can say that the denominator is in the form of 5 power n into 2 power m only. So it has a terminating decimal. So it has a terminating decimal. Now moving to the question number 5. The question number 5 says 9 by 30. 9 by 30. I am writing 9 as it is. Let us do the prime factorization of 30, because 30 is not a prime number. 2 15s are 5 3s are 3 1s are. So that is 2 into 5 into 3. Now as I said previous onwards, if the denominator is in the form of 2 power n into 5 power m, or else in the denominator only number 2 should be there, or only number 5 should be there, or both 2 and 5 should be there, except that nothing. So in these cases we will say that it has terminating decimal, otherwise non-terminating, right? So let us observe the denominator here clearly once. Here number 2 is there, which is required for us. Number 5 is there, which is required for us also. But here something else is there, that is 3. So now before going to the conclusion, just conclude one thing, that is any cancellation is possible or not possible. Here 3 1s are 3 3s are possible. So now whatever is remaining, write that 3 by 2 times 5. Now if you observe clearly, in the denominator we have only 2 and 5. So the denominator is in the form of 2 power n into 5 power m. So it has a terminating decimal. Question number 4 is finding decimal without division. So for this 2 methods will be there. So I will explain both the methods. So which one you are feeling easy, go with that one. The first one is given as 1 by 2. So what we need to do is, without division to find out a decimal, we have only one method which is very easy. That is making the denominator 10 or 100 or 1000 or 10,000 and so on. Like this, only 0 numbers. In the denominator, if we have 10 or 100 or 1000 or 10,000 or lakh, 10 lakh, crore, 10 crore, something like this, only 0 numbers. So it is very easy to write the decimal. So that is what we need to do exactly here. Now here in the denominator we have number 2, right? 2 table where we will get 10. So 2 5s are, right? So multiply and divide by 5. So we will get 5 1s are 5 by 5 2s are 10. What is the value of 5 by 10? 0.5. That's it. Let's take the second number then. 3 by 4. Again same. In the denominator, we need to make either 10 or 100 or 1000 or 10,000 and so on. Now if we observe the denominator 4, in 4 table, we won't get 10. So cross it out. Next number is 100, right? So in 4 table where we will get 100, that is 25 times. So multiply and divide by 25. 25 divided by 25, that is equals to 25 3s are 75 by 25 4s are 100. 75 by 100, 0.75. Next, coming to the 40 table. So I mean, sorry, third one. 7 by 40. 7 by 40. Okay, here the denominator we have 40, right? Now 40 table where we will get 10, obviously we won't get, so cross it out. Next 40 table where we will get 100, we won't get, so cross it out. Next 40 table where we will get 1000, then we will get 1000 in 40 table near 25 times. So multiply and divide by 25. So that will be 25 times 7. 175 divided by 25 times 40,000. 175 by 1000 is 0.175. This is the first method. Then what about the second method? Let us check here once. 1 by 2, right? First one, 1 by 2. In the denominator we have only 2, that is only just one time, right? So we need to multiply with 5 also one time. How many times 2 will be there? Those many times 5 we need to write. How many times 5 will be there? Those many times 2 we need to write. So in the denominator we have 2 only one time. So just multiply and divide with 5. That 2 one time only. 5 ones are 5 by 5 twos are 10. 5 by 10, 0.5. Coming to the question number 2, 3 by 4, right? So 3 by 4. First 3 by denominator 4 is not a prime number. So let us do prime factorization of 4. How it will be? 2 twos are. Now observe the denominator clearly. In the denominator we have 2 times. So 5 also should be 2 times. So multiply with 5 into 5 by 5 into 5. So that will be 5 5 is 25, 25 3 is 75 by 5 5 is 25, 25 is 2 are 50, 52 is 100. 75 by 100, that is same as 0.75. Coming to the question number 3, 7 by 40. 7 divided by 40 is equals to 7 by denominator 40 is not a prime number. So let us do the prime factorization of 40. 5 8s are 40, 2 4s are 8, 2 2s are 2, 2 2s are 4, 2 1s are 2. So that can be written as 5 into 2 is 3 times, right? So I am writing it as 2 power 3, or else you can just keep it as 2 into 2 into 2 also, no worries at all, same will be. Now if you observe the denominator, in the denominator 2 is there 3 times. So if 2 is there 3 times means definitely 5 also should be 3 times, but here 5 is only 1 time. So still we require 2 more. So that's why multiply with the 5 into 5 by 5 into 5. That is equals to 5 5 is 25, 25 5 is 175 by, here 5 is 3 times, 2 is 3 times, right? So that can be written as 5 cube into 2 cube. So that is equals to 175 by 5 cube into 2 cube. 5 2s are 10 power 3. 175 by 10 cube, 1000. 175 by 1000, that is 0.175. Use division algorithm to show that the square of any positive integer is of the form 3p or 3p plus 1. So we have a formula, right? A equals to bq plus r. So by using that formula we will solve this one. But before that, just one small step you need to write, that is let a be any positive number, any positive integer. So we know the formula A equals to BQ plus R. Now what is this B value, R value, Q value, all will be there in the question itself. So let us try to find it out. Here 3 is given, right? The 3, that value is nothing but B value. So B is equals to 3. If B is 3, then what are the reminders? Always reminder will start from 0 and it will be less than the divisor compulsory. So here the divisor is 3, then remainder starts from 0. So 0, 1 and 2. So reminders are 0, 1, 2. Now let us substitute this 1 by 1 remainder in our formula A equals to BQ plus R. So A is unknown as it is, you keep equals to BQ plus R is our formula, right? So A is equals to, in the place of B, number 3, Q as it is, plus. Here we have 3 reminders, right? So let us substitute one by one reminder. First I am going with the remainder 0. So in the place of R, keep 0. So A equals to 3Q plus 0, 3Q. Now what is saying in the question? Square of any positive integer. So let us do squaring on both the sides. SOBS, squaring on both the sides. So that will be A square equals to 3Q whole square. 3Q whole square, it means this square is applicable to the number as well as to the alphabet. So 3 square is 9, Q square as it is. So A square equals to 9Q square. So now what I will do is, in the question is asking to show that it is in the form of 3p plus 1. So it means number 3 I require. So that's why from 9Q square I will take out 3 common. Then what we remains with? Again 3Q square. So now I can say that it is in the form of, it is in the form of 3p. It means this total bracket I am replacing with the alphabet p. So 3p, where p is equals to, what is there inside of the bracket? Write that one, 3q square. So we completed with the 0 remainder, right? Now let us go with the another remainder, that is 1. Same formula as it is, A equals to BQ plus R, A as it is, B value is 3, Q as it is, plus. So 0 remainder completed. Now we are going with the 1 remainder. So A equals to 3Q plus 1. Now according to the question we need to go with the square, right? So again as usual, squaring on both the sides. So what it will become then? A square equals to 3Q plus 1 whole square. Left side A square as it is, and right side if you observe 3Q plus 1 whole square, it is in the form of A plus B whole square. So A plus B whole square formula is A square plus B square plus 2AB. So let us expand this. 3Q plus 1 whole square is 3Q whole square plus 1 square plus 2 into 3Q into 1. That is equals to 3Q whole square. Again, this square is applicable for the number as well as for the variable. So 3Q whole square will become 9Q square plus 1 square is 1 plus 2 into 3 into 1 is 6Q as it is. So we got it as 9Q square plus 1 plus 6Q. Now what I will do is, I will write this 9Q square and 6Q together and 1 separately. So that will be 9Q square plus 6Q plus 1. According to the question, everything should be in the form of 3p plus 1. It means number 3 should be there, right? So from 9Q square and 6Q, I will take out 3 common. So what it will become then? 3 3s are 9Q square plus 3 2s are 6 it will be. So plus 1 again I am writing separately. Now if we check this one, this is in the form of 3p plus 1. This bracket whole I am replacing with the variable p. So where p is equals to, what is there inside of the bracket? Write that as it is, 3q square plus 2q. So 0 remainder completed, 1 remainder completed. Now let us move to the remainder 2. The formula which we have is A equals to BQ plus R, right? So A as it is equals to B value is 3Q plus and remainder is 2. So now squaring on both the sides. So we will get A square equals to 3Q plus 2 whole square. So left side part as it is, 3Q plus 2 whole square, it is again in the form of A plus B whole square. So A plus B whole square is A square plus B square plus 2AB. So that will be 3Q whole square plus 2 square plus 2 into 3Q into 2. That is equals to, this square is applicable for number as well as variable, right? So 3 square is 9, Q square as it is, plus 2 square 4 plus 2 3s are 6, 6 2s are 12Q. Now according to one logic we know that always the remainder will be smaller than the divisor, right? So according to the divisor, we know it is 3. So this we need to separate it as 3 plus something, or else 3 multiple plus something. So that's why I'm writing it as 9q square as it is, plus 4 we can write it as 3 plus 1 plus 12q. Again writing 9q square, 12q and 3 together and plus 1 separately. So we will get it as 9q square plus 12q plus 3 plus 1. Now from these three terms we can able to take out 3 common, right? So let us take out 3 common. So we remains with 3q square plus 4q plus 1. Again this plus 1 as it is. So now again it is in the form of, it is in the form of 3p plus 1. This total bracket I am replacing with the variable p, where p is equals to 3q square plus 4q plus 1. Moving to the equation number 6. Check whether 6 power n can end with the digit 0 for n belongs to natural numbers. To be end with digit 0, it should have 2 and 5 as prime factors. So now he is speaking about the number 6 power n, right? 6 power n is equals to 6 can be written as 2 3s are power n as it is. So any number, if it needs to be end with the digit 0, definitely it should have 2 as well as 5. Both, I repeat, 2 and 5. Both should be there compulsory in the prime factorization. Here, if you observe this, number 2 is there, but number 5 is missing in this one. So we can say that it won't end with the digit 0. So the same we will write it as 5 is not a factor, because 2 and 5 both should be there, right? So 2 is there already, but 5 is missing. So as 5 is not a factor, 6 power n cannot end. 6 power n cannot end with digit 0. Next, moving to the question number 7. What is the last digit of 6 power 100? 6 power 1 is 6. 6 power 2 is 36. 6 power 3 is 216. Now if we observe clearly the last digit, 6 power 1 last digit is 6, 6 power 2 last digit is 6, 6 power 3 last digit also 6 only. So always 6 power n will end with the digit 6 only, where n belongs to natural numbers, because we are substituting for 6 power 1 onward. So starting from 1 means it is natural number system, because if you go with 6 power 0, then it will be 1. So last digit is changing then. So that's why we will go with the natural numbers onwards. So always 6 power n will end with the digit 6 only. Next, convert log 32 base 2 equals to 5 into exponential form. So he gave logarithmic form, that as log 32 base 2 is equals to 5. He is asking us to convert this logarithmic form to exponential form. It's very easy. Log 32, so main number is 32, right? Write that 32 as it is equals to, here it is base, write it as it is as the base only. This answer will become our power. So log 32 base 2 is equals to 5. In the exponential form, it is written as 32 equals to 2 power 5. Coming to the question number 9. Convert 3 power 4 equals to 81 into logarithmic form. Now in the question itself, exponential form is given. Then we need to convert that exponential form to logarithmic form. So we will given as 3 power 4 equals to 81. 81 is the main answer, right? So for that, keep log 81 is equals to power, you write it as the answer. Here base is 3, right? So write as it is as the base only. So if we convert 3 power 4 equals to 81 into logarithmic form, it will be log 81 base 3 equals to 4. Question number 10. Expand log 32 divided by 125. Log 32 by 125 is equals to, now this is in the form of log a by b. What is the formula for log a by b? Log a minus log b. So in short terms, if we say in logarithms, division will become minus. So the same way, log 32 divided by 125 can also be written as log 32 minus log 125. In logarithm, division will become minus. Now log 32 is the rate, so 32 prime factorization 2 power 5 minus log 125 prime factorization is 5 power 3. Again, in logarithms, power will come to the front, power will come to the front. So it will become 5 times log 2 minus 3 times log 5. That's it. We cannot simplify anything. So the expansion of log 32 by 125 is 5 log 2 minus 3 log 5. Moving to the next question, write 2 log 3 plus 3 log 5 minus 5 log 2 as a single logarithm. So in the previous question, we did the single logarithm as the expanded form, but in this case expanded form is given already, that we need to convert to single logarithm. So let us check it out. 2 log 3 plus 3 log 5 minus 5 log 2. So the main formula which you are going to use in the first step is log a power m is equals to m log a. So what exactly this formula is? In the logarithm, for the main number, if power is there, means that power will come to the front side. So if I speak about the same formula in reverse, that is, in front of the logarithm, if any number is there, means that number will come as the power for the main number. So this second logic I am going to use, that is, front number will come as the power, front number will come as the power, front number will come as the power. So we will get it as log 3 power 2 plus log 5 power 3 minus log 2 power 5. So if we write it as log 3 power 2 is 3 3s are 9 plus log 5 power 3 is 5 into 5 into 5 125 minus log 2 power 5 is 32. Now again one more formula which we will use is, in logarithm plus will become multiplication. So log multiply both the numbers minus log 32 as it is I am writing. This I will solve in the next step. Next, log 9 times 1125. Sorry 125 it is. Okay, 9 times 125 it is 1125 minus log 32. Again, in logarithm, minus will become division. So log 1125 minus log 32 is log 1125 divided by 32. Moving to the next question, if x square plus y square equals to 25xy, then prove that 2 log of x plus y equals to 3 log 3 plus log x plus log y. In this, if we observe the question clearly, we will get a logic what to do. So observe it clearly. In this total, what is asking to prove, plus term only there, minus term is not there. So whenever if minus term is not there, go with adding 2xy. If any minus term is there, means go with subtracting 2xy. Remember this very clearly. Okay. Now let's take the given equation, that is x square plus y square equals to 25xy. X square plus y square equals to 25xy. So whatever is asking to prove, in that every term is positive term only, right? So add 2xy both the sides. Add 2xy on both the sides. So then it will become x square plus y square plus 2xy is equals to 25xy plus 2xy. Now if you observe the left side part clearly, x square plus y square plus 2xy, that is in the form of a square plus b square plus 2ab. So a square plus b square plus 2ab is nothing but a plus b whole square. So the same way, x square plus y square plus 2xy is x plus y whole square. 25xy plus 2xy, 27xy. Okay, now in the beginning I said that two logics will be there, right? So one logic is observing this one, what is asking to prove in that every term is plus term. So that's why we are adding to xy. What in case if we forget that logic, then what is the next logic? So that is very easy. As we discussed in the previous question, the main number which is in front of the logarithm, it will go as the power, right? So then that will become log 3 power 3, right? So log 3 power 3 is nothing but 27, right? So 27 number should be there, but in the question we have only 25, right? So it means 2 more we require, so that's why add 2xy. This logic also you can use. So adding 2xy we did, and then after in the question whatever he is asking to prove in that logarithm is there, but in this step we don't have any logarithm, so that's why apply log both the sides now. So applying log both the sides. So what it will become then? Log of x plus y whole square equals to log 27xy. In the logarithm, power will come to the front, right? So the same way, this 2 also will move to the front. So it will be 2 log of x plus y equals to log 27xy. Left side we can do nothing, so just keep the left side part as it is. 2 log of x plus y equals to log 27xy. 27xy, it means 27 into x into y. In logarithm, multiplication will become addition. So log 27xy can be written as log 27 plus log x plus log y. Again, writing the left side part as it is. 2 log of x plus y equals to log 27. Prime factorization is 3 power 3 plus log x plus log y. Left side part as usual. 2 log of x plus y equals to, again for main number power is this, so it will come to the front, then it will become 3 log 3 plus log x plus log y, hence proved.